I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Jam, are you ready to hear what you're going to learn about today?
I'm very ready.
Okay. So we had a fire in our backyard yesterday.
On purpose, right?
On purpose in our fire pit.
Okay. Whew, that's good.
So we had a fire in our backyard and we noticed that the dogs we could see their breath when they were breathing out. But it wasn't really that cold. Like I would say it was maybe in the 60s tops, or I guess maybe in the 60s at the lowest.
Okay.
So it didn't feel cold enough to be able to see our breath in the air. And we were talking about that around the fire. And then I realized I didn't really know at all what it was when we saw our breath in the air.
Yeah, I've wondered that too. I feel like I have been surprised. We're all used to that happening at really low temperatures, but I've been surprised whenever it happens at kind of medium temperatures. And I'm like, huh.
Okay. Well, I'm going to tell you why that happens.
Okay, sweet.
So there's two things at play here. And the first is the conversion from solid, liquid, gas. So let's talk about solid, liquids, and gases, okay?
Okay.
At the molecular level, solids have the least energy. So they're not moving around very much. So they're not capable of their atoms breaking apart from each other and flying away the way gases do. Because there's just not very much energy in them. It's kind of like if you have a pile of sleeping dogs, there's not going to be one that gets up and suddenly sprints off, you know?
Okay.
Because they just don't have a lot of energy. So that's why they stay in a solid mass.
Yes, they've already been playing a lot or something, and so they're just exhausted.
Exhausted.
It's all gone.
And then if you get a little bit of energy, you're maybe waking up first thing in the morning, your dogs are starting to stretch and yawn, whatever. That's when you're in the liquid state.
Okay.
So liquids have more energy. They're capable of some motion, but not, again, going to fly away and totally separate out. The highest level of energy is in the gaseous state. When your liquids turn into gas is because the molecules have gotten enough, or the atoms or whatever, have gotten enough energy to spread apart from each other.
Okay.
So they're high energy. They have enough energy to be moving around in the air instead of condensed down in the liquid state, or even colder in less energy in the solid state.
Okay.
Okay.
Right.
So when you breathe, there's a lot of water in our breath naturally. And generally, we breathe out and we don't see anything because that water that's in the gaseous form already can stay in the gas form, in the vapor form, out in the air. And it just stays in the vapor form and goes away and leaves us.
Okay.
But when we breathe out and we can see our breath, what we're seeing is those water molecules that are in the gas state are condensing down to a water immediately. And we see the water in its liquid form hanging momentarily in the air before it dissipates off.
Okay. So does it go back to a gas after that? Is it like...
I wasn't 100% sure on that, but here's why it does that. There's two reasons.
Okay.
One, if the air is sufficiently cold, that will reach the point where the water molecules have lost enough energy to go from gas to a liquid. Because, as soon as you get something that's warmer in a space where it's surrounded by less heat, it tries to even out the heat. We talked about that in our episode about the vacuum insulated flasks and how they work.
Right.
So that's one option, is that as you breathe out, it's cold enough that the energy is lost and it's going to condense down to the liquid state.
Okay.
But there's another piece of it too. And that's if there's too much water already in the air in the form of water vapor or the water gas molecules in the gaseous state. it's like there's not enough room for any more water molecules in that gaseous form to get into the air.
Oh, I see.
And the thing that it reminded me of is, when you're dissolving sugar in your tea and you eventually reach a point where you've dissolved all the sugar it can take, and no matter what you do, no more sugar is going in. It's saturated. That's the same thing that happens with the air. It will be saturated with water. So when you breathe out and try to add water to the air, it can't take it. And so it's not going to go into the gas form in the air. It's going to condense out in the liquid form.
But it could take more if the air was warmer?
Yes. So that's another thing that's similar to if you have tea and it's hot, it's going to dissolve more sugar more easily than if you have a cold tea, right?
Oh, gotcha. Okay.
Or the same thing with if you try to use honey in hot coffee versus cold coffee. In cold coffee, that honey basically just turns to a brick. It's not going to go into that.
Yeah.
But in hot coffee, it'll dissolve right into it.
Right.
So it's almost like this piece of it is twofold. One, it depends on how much water vapor is already in the air. But two, if you have warmer air, there's room for more water vapor than if you have colder air.
Right. Okay.
So if you breathe out and you can see your breath, you know that the air around you is fully saturated with water. It can't take any more water, and it's sufficiently cold that it can condense down.
Wow. Interesting. This might be obvious too, and I've definitely feel like this is how I've experienced it, but does that also kind of mean that when it's cold, it kind of can't be humid?
It can be humid, but it can be less humid, I think. The relative
of humidity
is lower.
Okay. Interesting.
Yes. So I think that's why we can feel more water. It's easier to feel like the sensation of water because there's less able to stay in the air, even if it's technically the same amount of moisture.
Right.
And I tried to look into why that's true. And I think that it is because of how much those vapor molecules move around. So if it's hotter, they're taking up more space. They're spreading out more. There's more room in the air physically, because technically the atmosphere is just empty, and then there's water molecules and nitrogen molecules and oxygen and all that stuff moving around in it. So I think that if it's warmer, they're moving around more, they're more spread out, there's more space than there would be if they're colder, bunched up, not as much energy, not moving around as much. That's what I suspect, just based on my knowledge of how molecules move and temperatures.
Yeah.
But I could not confirm that anywhere. So that's pure speculation.
Okay. Dang, interesting.
Okay, so that's it. I know. I was like, that's so interesting. It's sort of like what happens when we try to dissolve sugar in water only with our breath.
Yeah. And what's crazy is that it's really simple in the sense that I feel like these are the kinds of things that just the building blocks of what it takes to understand this are some of the earliest things I think a lot of us learn about chemistry and science, about the slight differences. I know it's kind of been explained at different levels to me as a learner over time about solid liquids and gas and stuff. And then you kind of get a little bit of I feel like I remember learning a little bit of how that relates to weather sometimes, but not like a ton, And so I feel like there's just enough. It's a simple enough explanation that it kind of like didn't have to go way into the depths of chemistry to explain it. It's like, no, it's kind of these things we all sort of know about are what make this happen. It's kind of crazy.
Yeah, and I think it's sort of like a new application of things we already know about, because it's hard for me to think about, and I don't think it's technically right to say that the air can only hold so much water vapor, because what does it even mean for the air to hold things?
Right.
That doesn't really make sense.
Yeah.
In the same way that it makes sense to hold a certain amount of something in a cup. It's not exactly the same, but it is a similar concept of it. It can only take so much. You can only put so much into a space before it's full.
Yeah. Especially the space right in front of our heads. Like,
right.
Obviously, we're not talking about all the air everywhere, But right here, there's a sudden burst of new moisture or I guess really gas in the air, but water. Right. And it's like, oh, hey, we can't really take more of this right now. And also, we're colder than you are.
Exactly. And that's what happened with our dogs is even though it was not maybe as cold as you would expect to have to see that breath, it was cold enough to condense and the air was saturated enough so that we could see it.
Yeah.
Which then did make me wonder, does that mean if the air was fully saturated at 100 degrees Fahrenheit, which I think would be close to like 37 degrees Celsius, then would we be able to see our breath at that point? And I think it'd be very hard for the air to be fully saturated. But I think theoretically, if that was possible, for the air to be fully saturated, if you were maybe in a closed space and you tried breathing out at that point, I think it's possible. But I don't know 100% because technically then it would be warmer outside than it would be in us. So I'm not sure our breath would be losing energy. So then that gets in there as well.
Right.
But that's kind of a fun theory question to think about. In perfect conditions, if we could control everything, would that happen?
Right.
And I'm not sure the answer.
Yeah, interesting.
Maybe someone smarter than me or better at weather or this type of chemistry knows the answer, but I don't know for sure.
Yeah. Okay, so let me take a crack at trying to explain this back.
Okay, great.
I don't think I have a great analogy compared to dogs moving around or sugar in the tea. To me, that feels like just so perfect because it's a limit we've all experienced in something. And maybe you don't drink tea, but we all have something we've tried to put sugar in and we've hit some sort of limitation with that.
Yeah.
So our breath always has water in it that is in its gas form.
Yes.
And that's always the case. The thing that does change is the air that we are breathing our air out into. So whether we're inside or outside, whether it's colder or warmer, whether there's a lot of moisture in the air or not, those are the things that change throughout the year.
Yes.
So one thing, I think it's the second thing you said, is when we breathe out, the air we're breathing into has a lower, because it's colder, has a lower threshold of how much moisture, moisture it can take in gas form, kind of like having cold tea. The amount of sugar that can be dissolved into it is going to be at a lower level than if it was hotter, which we've talked about in a few other things. And then the other thing, I guess, is that being colder air and our air being warmer, our air, that gas is at a higher energy level. And obviously, because it's in gas form and also at a higher temperature, that as soon as it's going out into the colder air, it is reaching that ceiling of how much gas can we take that's water in its gas form, and also trying to level out those two very different energy levels because one's hot, one's cold.
Yes. So there's the factor of it will lose energy by nature because something that's cold is really simply the absence of energy.
Right.
The absence of heat energy.
Yeah.
So when your hot breath hits the cold air, automatically the hot breath is losing energy. It's dissipating. The energy is dissipating out because it's trying to really reach an even place where everything has roughly the same amount of energy.
So as it's happening, all the excited, just kind of spread out water particles, water molecules in the air that we're breathing out start to lose energy. And so they start to have to come together. They don't have as much excitement to be spread out anymore because a lot of the energy is being spread out into the air that was lower energy. And so they're suddenly not having the ability, the energy to spread out much like they were. And so they kind of come together. We start to be able to see it. But it's funny because it's still, I think to a lot of us, we think that kind of still seems like gas in a lot of ways because it's still floating out there.
Mm-hmm.
But it's just these,
it's hanging in the air.
Yeah, just these tiny condensed bits of water that we previously would not have been able to see. Like we're not seeing our breaths all the time walking around inside, you know?
Right.
If you are seeing your breath inside, you should turn your heater on, dude.
Yep, that's right.
Did I?
So it's just, oh, go ahead.
I was going to say, did I kind of get it? That was like probably the messiest explanation I've ever attempted because I was trying to both, one, wrap my head around it, and two, I think it's hard too, is that it's hard for me to actually draw a neat line between the two main reasons that this happens because it seems like they're just so interrelated.
Yeah, and I agree. I think it was a hard concept because it's not just about if it gets cold, it'll condense. It has to be under the right conditions for it to also condense because it's the right temperature. Mm-hmm. And I mean, just to really, really simplify it down, you can say it's just condensation of the water molecules in our breath. So just exactly like on a hot day when the air with moisture in it hits your cold cup, you get condensation on the outside. Mm-hmm. That's the same exact concept for what's happening when we breathe out and can see our breath, but the conditions have to be just right for that to happen. So that's kind of the complicated part is the conditions. And I'll say it was even hard for me to explain that. Mm-hmm. So I don't want you to feel like, I did a messy job. It's just kind of a weird one to wrap your brain around. The building blocks are simple, but the individual concepts are a little bit more complex when you try to explain them.
Yeah. Yeah, it really is weird.
And we talked about before that if you can manipulate the pressure of things, then that will change the boiling point and that can change the melting point of things. And so I suspect as well that there's something about pressure going on. The vapor pressure of all the water molecules that are already in the air make it to where it can't turn into vapor or something. You know, it's a little bit more complex than even what we talked about. There's even more questions that I have that weren't clearly answered in the resources I found. But I think the basics we can talk about. And so we see the condensation and we know it's because it's cold and the capacity for the air to hold moisture is lowered. And when things are cold, warmer things will lose their heat energy to the cold surroundings. And all that together means the moisture in the air that we breathe out condenses down into those cool vapor clouds.
Dang. Very crazy.
Very crazy.
Also,
so that's why we could see the dog's breath is also because it had rained earlier that day. So the air was full of water.
Oh, interesting. Yeah.
Yeah.
One of my favorite versions of this to see is that I feel like at moderately cool temperatures all the way to being very cold, obviously we see our breath, but when I walk outside with a cup of coffee that was just kind of a little bit steamy inside, and you go outside, it's like way more. Instead it just looks like, what witch's brew do you have brewing in that miniature cauldron over there? It just seems like really dramatic. The colder it gets, it's kind of crazy.
Yeah, that's definitely a good similar concept. That's just a little bit more dramatic, and because the coffee's hotter and that there's more just of those water molecules in it, it's probably easier to see and more of that steam and stuff gets created. So great. Well, thanks for that little recap. Is there something in your week you want to recap for us as well?
Yeah, it was kind of fun this week. We were able to have a socially distanced fire pit hangout at your house.
Yeah, that's right.
And my little son was pretty enthralled by the fire.
Oh my gosh, he really was. It was very cute.
Yeah, it's just funny because he's definitely seen fire, but it was dark outside. And obviously the glow and majesty of fire is so much stronger whenever it's outside and it's dark. And he was just like smiling, looking at the fire. And, the kids' ability to see when they're that young is pretty low, but like something that obvious is just, doesn't matter how good or bad your vision is, it's probably still going to be impressive, the glowing, something like that. And he just loved it. So that was really funny just to see him continually smile over and over and over about this fire. Mm-hmm. But also just fun to get to hang with people, and fun that it was cool enough weather to have a fire, and just that kind of stuff that is fun and seasonal. And I've been kind of bummed because of how early it gets dark now. A lot of outside hangouts are a little harder to do, or they are just less ideal conditions. Hanging out in the dark at like 7 p.m. with somebody, or like going on a walk or something like that, it's just not nearly as fun. It's like, I don't even want to be walking around in the dark right now. And hanging out around a fire, though, is really cool. And so that made it probably one of the more fun, like, evening hangouts I've been able to do in a while. So,
yes, we've definitely utilized our fire pit quite a bit. It's been really, really fun to have that, because with COVID, we're trying to be safe. We're trying to be social distanced. We're trying to still see our friends and be mentally and emotionally healthy. So having a warm fire outside seems like a really good way to do that. So it's been really great, and I'm really thankful that we have that.
Dude, yeah, that was fun. Well, what about you? What recap from your week do you have?
Well, I already talked about my fire pit a little bit, so that's been really fun for me too. So honorable mention, but I have been using You Need a Budget. Jam suggested it, and for college students, you can get a 1-year subscription for free. Mm-hmm. And I'm technically still a student, so
yeah, that's any level of student. They are cool with it being like, undergrad, grad, your third degree. Who knows? It doesn't matter. They don't care.
Well, I love it, and I'm really thankful for it, because I've always had a strict budget, but it is at times hard for me to sit down and look at how much is in every single category all the time. Because I am a grad student, so I'm busy and I don't have time to sit down and think through all that stuff constantly. And it makes it so easy to categorize my budget. It makes everything in that way so easy, and it's very exciting because I know for sure what I have money for and what I don't. It's a little hard because I always go over in a few categories, but there's other places I can take from, and I put a little bit of cushion in there. And so it's just been really great. I am very thankful for that budget app. I feel more in control of my money than I have, and it's so low maintenance.
Yeah.
It's so easy. It was a little bit of work to get it set up and understand it. And then once I did in October and November, I've been able to save a lot more money than I have for a while. It's just been really good. So I'm really, really excited about that app. And I think everyone should probably get it. Just be patient as you figure out how it works. But oh my gosh, it was so worth it.
Yeah, dude, I'm so glad to hear that. That is so cool. And that relief that you're talking about is exactly how I felt also. I started using it in August, so just like a couple months before you, and already became a huge believer in just that short period of time, to the point where I was recommending it and nerding out about it on the podcast and stuff. But that is so cool. I'm so glad that it's been so helpful for you.
Yeah, it's just really nice because when I'm doing my budgeting now, I know for sure that the money is there because my transactions are always being updated. So I'm always deducting money from different categories as the spending comes in. And it's just really exciting. If I want to buy something, I can just look and see if I have the money. And if I have it, I have it. And if I don't, I don't. And that's just been really, really cool. So
yeah, dude, that's nice. That is it makes a huge difference. So this is not an official sponsorship by the show, but individually, Melissa and I both love YNAB.
100%. So thanks, Jam, for teaching me about it and getting me excited. I love budgeting, so this is very exciting. And thanks for coming and learning about why we see our breath in the air. I love teaching you guys, so it was very exciting.
Dude, thanks for teaching us, and thanks for loving budgeting. And and Melissa and I have a lot of ideas like breath, seeing your breath in the air, chemistry things like that in everyday life. But we want to hear from you. If you have questions or ideas, you can reach out to us on Gmail, Twitter, Instagram, or Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the cost of making it, go to ko-fi.com/chemforyourlife and donate the cost of a cup of coffee. If you're not able to donate, you can help us by subscribing on your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us to be able to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jerem Robinson. References for this episode can be found in our show notes or on our website. Jerem Robinson is our producer, and we'd like to give a special thanks to V. Garza and A. Collini, who reviewed this episode.